Hello once again. Our next speaker is Danica Porobic. She is a principal member of the technical staff at Oracle America, and she's currently working on database and management technologies. Now, her talk will talk about engineering database hardware and software together. We'll focus on Oracle Autonomous Database, which is a premier cloud database that combines automation techniques and database infrastructure development. So this talk will provide a brief overview of ADB and go deeper into some of the innovative uses of modern hardware technologies to deliver high data access and low latency data modification performance. So without further ado, and also don't forget to ask questions in the chat, I will now give the word over to Danica. Enjoy.
Thank you very much, Ognjen. It's my pleasure to be here and to spend the next 20 minutes or so telling you about some of the cool stuff that my team at Oracle is working on to provide best-in-class database services built on highly tuned platforms. And I will follow the theme of balancing hardware and software together, and in this talk put emphasis a little bit on one example where persistent memory and fast networks are used together to significantly improve performance. But before I go there, I would like to spend a little bit of time to tell you about myself and where I come from. So, as Ogden mentioned, currently I'm principal member of technical staff at Oracle, working for the database in-memory team on optimizing data access methods. And before that, I spent 6 years at EPFL working on scaling up transaction processing system architecture for a non-uniform hardware platform. So it's been about a decade of me working on making sure that our data management systems are tuned to the modern hardware and making the best use of it. And before, I spent some time at Microsoft working on SQL Server, which is where I got my start in data management and databases. And before that, I worked for 2 summers at Windows while studying in Novi Sad. So in this theme of connecting research in academia and industry, I'm kind of taking the departure from a previous speaker and shifting focus from applications and for us data management system people, machine learning and data science are applications, and going level down to the systems. And the aspect of the systems that I focused in my PhD thesis was the impact on non-uniform hardware topologies. And these days, when we basically run the world on this, mostly on these 2-socket systems, we really need to be cognizant of that. And to give you a flavor of how this looks like, I have here a schematic of a 2-socket server with different caches and different that are private to cores, and with last level shared caches, memory controllers, and inter-socket links. And what's interesting to software system designers who write multi-threaded software are communication latencies between these threads based on where they run in the system. So on the low latency end of the spectrum, we have 2 threads that run on the same processor core. And for this system that I have here, which was state-of-the-art when I was at EPFL, it was 12-core Intel Xeon E5 V3. Thread-to-thread communication latency when they run on the same processor core was 21 cycles, which jumped to 72 cycles if they had to go through L3 to exchange data, but when they had to go through inter-socket links, it went all the way up to 237 cycles. So just based on where two threads are running when they need to exchange data, we get order of magnitude difference in latencies. And actually differences have jumped since then as we got more and more cores in our modern processors, and the memory hierarchy became more complex. So why should we care? So to illustrate, and before I get there, I want to introduce you to the concept of hardware islands, which is a set of cores that communicate faster amongst themselves than with other cores in the system. And in this system, each of these processor was forming an island, but actually modern CPUs have multiple islands on the same die. Okay, so why do we need to care about this? So let's take a step back to kind of textbook view of transaction processing system design, where we have processor cores that process incoming transaction requests, such as deposit $100 or spend $5 on a coffee. So we have these processes or threads that are in the system that run on some core, and they access data that's stored in some either shared memory, shared disk, basically shared memory hierarchy. So when thread starts processing transaction requests to ensure consistency of data, it needs to acquire locks. Then it needs to, when this access is protected, it needs to go and access data, and also it needs to update the system state. And all of these accesses entail a lot of communication between these threads, because they're updating shared data structures, they're accessing the same data structures. So basically, because they communicate a lot, how they communicate is very important to their performance. And earlier, in my early part of my research, I was focusing on studying different deployment models of transaction processing systems using partitioning and try to understand how different workloads and different hardware topologies and different deployment granularities, which of them basically makes the best use of hardware. And we went in this exploration all the way from traditional shared everything, where we basically had one system managing all the data and having all processor resources, and it gave us stable performance for all kinds of workloads. Unfortunately, for many, it required a lot of communication, which was not optimal for performance. On the other hand, for workloads that we could easily partition, we got amazing performance because we eliminated a lot of this communication. And unfortunately, not many workloads in real life are actually perfectly partitionable. So for many workloads, it performed really badly. And islands sure not gave us something in the middle, but still it wasn't really enough to make the best use of hardware. So to get there, what I did later was exploring different designs for improving the performance of transaction processing systems by eliminating all the unnecessary communication, especially across sockets, across hardware islands, making sure that the system is adapted to both hardware and the workload that users want to run, and that if the workload changes, we're monitoring it, and we can quickly repartition. And coming from this academic background, it was easy for me to transition to Oracle database team and continue working on adapting the system to make use of hardware. So in the next part of the presentation, I will tell you how we do it with Exadata hardware platform powering the Oracle Autonomous Database. But first, I want to tell you what Autonomous Database is and why we brought it to the market. So this is premier cloud service whose goal is to make running mission-critical workloads easy. Traditionally, these workloads required an army of people to manage them, but with steady improvements over past few decades in infrastructure automation and database automation, plus with the automation of data center operations powered by machine learning, we can actually offer this mission critical service pretty much to anyone with any database workload that they want to run on this. And in the heart of this system is Exadata hardware platform. And here I have some, as we like to call them, speeds and feeds of the latest generation of Exadata X9M. And Exadata has been following this model that is now becoming even more popular in the cloud world of separation of storage and compute with the very beefy database servers, which in this generation have 64 cores and up to 2 terabytes of RAM for a 2-socket server and more for the 8-socket servers, and high storage capacity storage tier with either combination of flash and spinning disks or flash only for even higher performance. And what's really great in the latest generation are 2 new hardware technologies. The first one is this high bandwidth, low latency network that enables 100 gigabit RoCE, which stands for RDMA over Converged Ethernet, which enables really nice set of optimizations. One of them I will talk about in the rest of the presentation. And another really great new technology is persistent memory. And in this system, we have 1.5 terabyte of persistent memory. And the great thing about persistent memory is that it combines latencies that are similar, much closer to DRAM than flash, with persistence and high capacity, which is kind of closer to flash than DRAM. And its price is also it's cheaper than DRAM, so we can have this super fast persistent memory as another level in the memory hierarchy. So in the rest of the talk, I will illustrate how we use it in this latest generation of Exadata to accelerate transaction processing. So let's go under the hood of OLTP, which stands for Online Transaction Processing. And we will follow the story of our user that whom we'll call Ben, who had some money that he wants to deposit to his bank account. So let's see how this process of depositing money to bank account, which is one update SQL statement, is actually run in the system. So when this statement arrives in the system with this database request, system needs to parse it, basically to transform it from text into executable plan. And this is typically for most common operation already done, and it's cached, so it's just a memory lookup. So this is pretty cheap in the bigger scheme of things. And the first thing that this statement needs to do is to find Ben's account. And to do that, we traverse a B tree via primary key index. And indices are in general much smaller than data, and it's highly likely that they will be in memory. And so this is also very fast. However, once we got through the index, what we get from the index is identifier of Ben's account. So we need to find Ben's account, the data block that contains Ben's data, and update it. And here we get into trouble because Ben doesn't spend all day, transacting with the bank. So his data is highly likely not in memory. And there we hit IO cliff because we have to go to the storage. And what we do in technical terms is a random data read. So let's see how this looks like actually in the physical system. So we send a request from database server to storage server, which looks up its flash cache. And because it's maybe we find it, maybe we don't find it, maybe we need to go to the base table storage. But in any case, it will be a flash read, and then we send the data back to the database tier, and we put it into DRAM cache, and then we're back to in-memory processing. So how long does this take? And what does this entail? So to answer that, we'll kind of go one step lower level and actually look at all of the steps that are needed to do this. So basically, we start from, on the database server side, we start from database application, from the database system. Then we interact with operating system, that is with kernel drivers, with network drivers, to send requests to the storage server, where on the storage server side, we again need to involve drivers to process these requests. Then we get to storage server software to find, basically to interpret this request, and then we go to Flash to actually read it. And the read latency of that physical one block 8K random read from Flash is on the order of 100 microseconds. And how much do we actually take to go through all of these different levels of the software stack? Well, about 100 microseconds as well, for a total of 200 microseconds. I mean, it's pretty good, but we can do much better with the help of persistent memory and RDMA. So how do these two help us with avoiding this IO cliff? So the easy thing to do, the straightforward thing to do, would be to just say, oh, we have persistent memory so much faster, we're just going to replace Flash with persistent memory. Bam, 100 microseconds gone. But the problem is, we're still stuck with all of these servers, the software stack. I mean, so even if the latency of accessing persistent memory is 0, we're still stuck with 100 microseconds. So we actually need to do better. We cannot afford such complex software anymore in the era of modern hardware. So to actually make use of this really great low latency persistent memory cache, we actually need to skip all of these software layers. So to do that, what we do is use RDMA, which is remote direct memory access, over this low latency fabric to go directly from the application running on the database server down to persistent memory on the storage server. So when we do that, we actually eliminate this IO cliff. We get to latency of about 19 microseconds. So it's order of magnitude faster random read, and that basically translates to order of magnitude faster completion of the whole transactional requests. So to put it all together, we've passed through these first 3 steps that were in memory, but now we actually don't even need to deschedule running thread. We actually can just spin a little bit, and while we're waiting basically to get this block that we need to update back into in memory. And that allows us order magnitude lower latency. And that's just one of the things that RDMA and the persistent memory are used in a modern Exadata. With addition of persistent memory into storage hierarchy, we actually can use some of it for logging. So we get almost order of magnitude faster log writes, and we get a lot of IOPS, a lot of operations per second. So we get much higher bandwidth, so we can actually process many, many more transactions. And it's not just about transactions. After all, this is a data science conference, so we care quite a bit about analytics as well. And to just briefly give you a flavor of that, I'm going to show you a tweet from Bob, who's a database administrator. And what he's talking about here is how he likes using Exadata because it makes him very smart in the face of his peers. And what he's illustrating here is how a query that needs to access 600 and change gigabytes of data actually makes use of storage indexing to skip most of that because it's not relevant to the query. And then some of the processing is already done on the storage side, so we don't need to transfer the data out. So instead of transferring 600 gigabytes over the network, we can actually process most of it close to the data on the storage side and transfer only 284 megabytes that we actually need to complete the query over to the database side. And that's pretty much moving computation processing from closer to the data is kind of the magic of Exadata. And that's pretty much what also everyone else is doing when they design for cloud. And just to give you, a little bit more information about some of analytical features, the main one is offloading, basically moving processing closer to the storage servers, and also making use and building these columnar caches both in persistent memory and in flash, and that significantly increases processing speed so that we get to terabyte per second of data access, data scanning speed. And to achieve that, we actually need features that my team works on, which is in-memory columnar and processing and hybrid columnar compression, which gives us large space saving and also enables faster processing because we can do quite a bit of things also on compressed data. And this is done in every storage layer in the system for a balanced system. And with all of that, the reason why we do this is to achieve the mission of our company, which is to help people see data in new ways, discover insights, and unlock endless possibilities. So if you want to know more about this, I'll be happy to take any questions now, or you can also find me on Twitter or on my website, and I'll be happy to follow up. Thank you.
Hello, me again, and thank you for the insights into these technologies. There is, I believe, one question is, how intuitive are these technologies for new companies and new users once they, if they do decide to switch to these systems? How easy or let's say, what are the challenges of switching to the ADB?
So that's a really nice question. Thank you. Actually, for users, it's pretty much trivial. It's a database in the cloud that uses standard SQL. So all they need to do is to load their data, and then everything happens automatically. And I mean, it's not really. And the reason why it happens automatically is that this one system encompasses all of the learnings and developments from decades of experience running this, large mission critical business applications and running analytics for big companies. And to achieve this performance, we basically need to keep up with the latest generation of hardware, and also enhance the processing capabilities to support new and different types of applications. And kind of on the flip side, going back to my research and academic roots, if you want to build your own data processing systems or do research in this area, you should really think about the whole system and take a broader view, and not chase some benchmark and subspecialize, and you'll find really, really interesting ways to optimize systems.
Yeah, thank you for the answer. And going actually a bit on your research side, because you have quite a lot of experience with data systems in general, what are some of the smaller things that are better done here than perhaps in any other systems, rather than, let's say, the processing speed and stuff like that you already mentioned, but some of the smaller, more hard, let's say, in-depth issues that you saw that could help out, for instance, new users or just in general this system?
Yeah, that's a very interesting a question. So, I mean, from a usability point of view, there's a lot of the things that I haven't actually touched on here, where it's mostly system side, so it's all about performance. But actually, performance is very important for many situations, especially around data exploration and finding things from the data set that it's completely new to you. So basically, enable this interactive exploration is something that I would say is really interesting and kind of unique here. I'm not sure I'm answering your question, but I would stick to what I know well, which is performance.
Yeah, no, it is good. Yeah, that's it for the questions, and thank you once again for this talk. Some really nice insights and really nice answers as well. And I do hope that you enjoyed giving the presentation as well.
I did. Thank you very much for inviting me.
Thank you.